Okay. So, we have defined the language of propositional logic. We have talked about the syntax of propositional logic, we have talked about the semantics of propositional logic, and we have seen, for example, how you can represent certain knowledge base in propositional logic. Now, we want to talk about proofs essentially. Okay. So, and we will look at proofs in the context of propositional logic, and they will give us insights into proof in general, which we will carry forward to when you go to richer languages, because richer languages are the ones which are in fact more useful. So, in terms of logic, when we talk about true statements, we like to call them a theorem. So, for example, the Pythagoras theorem essentially. The Pythagoras theorem is called a theorem because we know that it is true essentially, and the task of a logician is to be able to derive it from certain sets of axioms. So, for example, in the case of Pythagoras theorem, you may be talking about Euclidean geometry. So, it has a certain set of axioms which are associated with that essentially, and then you should be able to derive that statement which is the theorem. The process of establishing that it is a theorem is called theorem proving, and it has been an activity which has been going on for the last 70 years, ever since computers were invented, and people have been writing programs to automatically generate proofs of theorems. Now, it is a syntactic process. Theorem proving is concerned with the syntactic process of constructing a proof. What is a syntactic process? It is basically you are doing pattern matching. You see a pattern and you are allowed to add something new to the knowledge base or to the set of sentences. There are many algorithms for theorem proving, many styles of theorem proving. We will look at a few of them in this course. The first one that we will see is direct proof, which is also called natural deduction, because that is the way that you would have written, for example, proofs in school, also sometimes called Hilbert style proofs. Or we will look at indirect proofs, or mostly we will see proof by contradiction, and we will look at two methods. One is called the tableau method and the other is called the resolution refutation method. But we will not look at the resolution refutation method in propositional logic. We will come back to it when we look at first order logic, because it shows its real power there essentially. So, we will begin with natural deduction or direct proofs or Hilbert style proofs. So, remember that we had this encoding of this story about Alice, or this knowledge base about Alice, and Alice likes maths, Alice likes stories, Alice likes algebra, Alice likes physics. These are the atomic propositions. Alice will go to college, Alice likes chemistry, Alice likes history. So, a lot of facts about Alice, and what we were told is that these formulas are true, that P and Q is true, which means Alice likes maths and Alice likes stories. P implies R is true, which means if Alice likes algebra, no sorry, P implies Q says P is Alice likes maths, then R is Alice likes algebra. So, if Alice likes maths, then she likes algebra, and likewise we had the other statements that were given in the story, but now we are working only with the propositional logic encoding of the story. So, that we can do symbol manipulation and come up with whatever we want to show. So, we often have a query over goal, and our query is going to be that is this proposition T, Alice will go to college, is this true? In other words, we are asking, will Alice go to college? So, let us look at how you would have done it if you were doing this in school, which is basically keep adding new sentences. So, in a direct proof, we choose rules of inference, we decide which rule we want to use and add the consequence to the knowledge base essentially. So, here it is. This is what is given to you. Alice likes maths and she likes stories and so on. So, this is a knowledge base that we are starting with essentially. We have not used one or two of those statements, because actually we will see that they are not, they do not play a part in the proof essentially. So, we have not written the entire knowledge base here essentially. We have just written what we need essentially. So, we first simplify, we take this formula P and Q and say we can get P and we can get Q out of it, and that is a rule of simplification that we had studied essentially. Now, to get Q, strictly speaking, we must first replace P and Q with Q and P, because the rule that we wrote said that the first element in the conjunction is something that you can infer essentially. Of course, we understand the semantics and we know that P implies P and Q is logically equivalent to Q and P, the rule of commutativity of and we could have replaced it there. But in this natural style proof of reduction, we must actually first add Q and P to the formula and then derive Q, but we often take the shortcuts and they are kind of acceptable. The program of course will not work. If you are writing a program, then you would have to introduce this step of adding this new formula Q and P essentially. Then we have R. How do we get R? Well, we have P here and we have P implies R here. So, modus ponens and we get R essentially. So, that is what we have written here from 2 and 5. So, 2 is here and 5 is here, and then we apply the modus ponens rules and we got it. Likewise, from 4 and 6 we got S. What does 4 say? 4 says is that Q must be false or S must be true, but we have said in 6 that Q is true. So, therefore, S must be true because Q is not false and therefore, we get S. Then we can use the rule of conjunction, which says okay, R is given to us, S is given to us. So, therefore, R and S is given to us, and then finally, we can use this statement number 3, which says that R and S implies T and therefore, we can infer T using modus ponens again essentially. So, this is the natural reduction style of proof or the direct proof that we often have been using during our study of maths in school and beyond essentially. We can also show the proof to be in a pictorial form as a directed acyclic graph, and so on the top row are the axioms, or not the axioms, these are the premises that have been given to you, and then the arrows show you how you arrive at new sentences. So, from P implies Q, you came to P, that was one thing we did. Then we also came to Q in a similar fashion, though I could have drawn, as I said here, Q and P as a new formula, and from this I could have drawn this, but we will take it with a little bit of flexibility here. Then from Q and not Q or S we can get S, from P and this thing we can get R, then from S and R and S we get this, and then from this we get this thing. So, this is just another way of showing the proof, and we will use this approach once in a while in our course here. Now, the interesting thing about maths is, or logic if you want to say, is that the proof is the product that is published. So, if you read the proof of, let us say, the Pythagoras theorem, then you are just looking at the final product, that this is the proof, these are the things given to you, and therefore, this is true, and therefore, this is true, and therefore, this is true, and so on. Finding the proof is another matter. That is where your effort goes into it. That is where your training as a mathematician or a logician goes to it, and that is something of course we are interested in, and we will see that finding a proof is essentially a process of doing some kind of search, which rule of inference to take and what facts to match it with, and what inferences to make is a process that we have to somehow automate. We are interested in automation here, remember. So, finding proofs, the proof of alpha, that alpha is a theorem that we have been trying to prove. The proof of alpha is the end product, that is the justification of the sentence alpha being true. So, we have the proof and therefore, we accept it to be true. It represents a chain of inferences linking the given facts to the desired goal or the conclusion essentially, as we saw in the directed acyclic graph a little while ago. Proofs are themselves found by a process of search essentially. Okay. So, there was this famous 4 color theorem. What is the 4 color theorem? It says that any planar map. So, you have regions or countries, if you want to say, all kinds of this thing. You construct any map that you can draw on a piece of paper, which is called a planar map, and you want to of course color them from different colors using because that is how we draw maps. So, this could be red, for example, this could be red, this could be blue, this can't be red or this can't be blue because it is adjacent to them. So, this should be green, for example, and then this can be yellow, then this can be, let us say, pink, and this can be, let us say, white, and this can be black, and this can be magenta. So, I have colored this map. What is the objective? To color it in such a way that you can distinguish between the different countries or regions essentially. What the 4 color theorem said was that if you have a map which can be drawn on paper like this, which means it is a planar map, then 4 colors are enough to color the whole map essentially. You do not need more than 4 colors. This theorem took a long time to prove essentially. Some things are like that, you must have heard about Fermat's last theorem and how for a few 100 years we did not have a proof for it, and eventually the logician Andrew Wiles found a proof. So, proof finding is not a straightforward process. It takes a lot of effort, lot of search, and in fact, the 4 color theorem was proved by a theorem proving program. So, which is why I have also mentioned it here essentially, and that program would have done some kind of exploration of what rules to apply in what order and things like that, and eventually come up with that. So, what happens is that you have done all this head breaking work. Apparently Andrew Wiles worked on Fermat's theorem for 20 years essentially, and then finally you present the proof which looks like a neat structure, but it does not show the kind of efforts that mathematicians put in trying to come up with a proof essentially. And if you look at the Pythagoras theorem, for example, there are many different kinds of proofs which have been given, which are creative, some much more creative than the others and things like that. It is only the final proof which is communicated or published essentially. This process of natural deduction can also be called as forward reasoning. It is a data driven chain of inferences. By data driven, we mean we start with the data and move towards the goal essentially. We will see later that there can also be goal directed search algorithms. But basically what this does is that you start with some data, you keep making inferences till the point where you have added the goal. So, let us say this was the goal in this particular problem, and then this is another problem that you are trying to see. What this does not show, that this only shows the final proof. What it does not show is that maybe you made some inference here, and then maybe you made another inference there, and then from this you made an inference there, and so on. All that is not shown. The trial and error that people do or programs do is not shown. What is shown is the final proof essentially. Now, that is our product that we want to produce essentially. So, this process is called forward chaining, in the sense that you are going from data towards this thing. Pick a rule with matching facts, add the consequent to the knowledge base, and you keep doing that till the goal is added to the knowledge base, and this process is called forward reasoning or forward chaining. We will compare it with backward reasoning or backward chaining when we move to first order logic essentially. The key question of course is which rule and what facts essentially. Okay. So, let us take another break here. We want to move towards other approaches to proofs, and we will start with the deduction theorem, which I mentioned in the past. I hope I did mention it before I mentioned it in the past, but in any case we will present it here and see that it gives us some additional tools for making proofs. So, we will do deduction theorem in the next video when you come back.